My name is Snyder, and today I'll be presenting emerging methods for short-chain PFAS sorption. So what are PFAS? PFAS are per- and polyfluoroalkyl substances, which are a diverse set of chemicals that all generally contain a fluorinated backbone, which makes these chemicals highly resistant to degradation. This resistance causes PFAS to easily accumulate in our environment, coining PFAS forever chemicals. Epidemiological and rodent studies have shown correlation between PFAS exposure and many severe health outcomes as shown on the graph on the right. Human exposure to PFAS can occur from consumer products as PFAS is used in industry to repel oil and water and change surface chemistry of consumer goods. Products such as food contact materials, textiles, personal hygiene products, and aqueous film-forming foam are a few product-based exposure pathways of PFAS. This type of direct exposure can be solved by diverting away from PFAS in manufacturing, but long-term PFAS exposure occurs from PFAS accumulation in the environment after primary exposure to consumer goods. Many products made with PFAS will degrade and contaminate the water systems. Drinking water has been identified as the most substantial exposure pathway for humans. So how do we prevent PFAS exposure from drinking water? Well, the current filtration methods, such as GAC, which stands for granulated activated carbon, are not good enough to filter out some PFAS. A household example of GAC is a Brita filter. GAC cannot absorb short-chain PFAS, which are the PFAS with small carbon backbones, since these PFAS are more hydrophilic and tend to prefer water than being absorbed by GAC. Our solution is proteins, which can specifically bind to these PFAS and absorb them from water. Immobilization and encapsulation on silica beads protects these proteins and allows for packing of these proteins in a filter.